This meeting is being recorded.
Okay, welcome to workshop 2. So I'm going to be going through the solutions to these ODEs, A through G, and so these are going to be these are all first order ODEs. We're going to be solving these using the different techniques we've learned in class. Okay, so let's get into it. Okay, so starting with the first equation here, A. Well, let's first identify the dependent variable. So y is the dependent variable. And that's significant because y appears only linearly in this equation, right? So y appears linearly. The derivative of y with respect to t, the independent variable t, is only there linearly, and all the nonlinear terms are with respect to t, the independent variable. So they can be nonlinear. So this is a linear ODE. Okay, and we can solve this using an integrating factor. We solve linear ODEs using integrating factors. Okay, so before we can do that, we need to rewrite this ODE in the standard form, okay? In the normal form. So the only problem we have here is with this term t, right? This term t here. So let's divide through everything by t. Okay, let's go. Okay, well, if I divide everything through by t, I get this equation here. dy by dt plus 2 over t times y equals t squared minus t plus 1 over t. Okay, great. And so the integrating factor, if you recall, we had something, the standard form, the general form, looks something like this. And so from this equation we can write down the function p, which in our case is going to be this 2 over t thing. Okay, so then remember our integrating factor is the exponential of the integral of p of t. So mu of t, the exponential of that thing. Okay, and so we can obviously easily integrate 2 over t. It's just going to be 2 times the log of t. And because we've got an exponential and a log here, we know that they are inverse functions of each other, so they can cancel out. But the 2 we can take using the exponential laws. The 2 we can take as an exponent. So we end up with t squared. Okay, so our integrating factor mu is equal to t squared. Okay, so then we know we can write down the solution for y. Y is equal to 1 over mu of t times the integral of f of t, which is the right hand side, times the integrating factor dt. So the integral of that product plus some integration constant c naught. Let's write down exactly what everything is here then. So 1 over mu of t is 1 over t squared times the integral of f of t. Well, f of t is the right hand side, so we get this t squared minus t plus 1 thing over t multiplied by the integrating factor, which is t squared dt plus some integration constant c naught. Well, this t squared here and this t on the denominator, well, one of those t's is going to cancel out, and we end up with the integral of a third order polynomial. So this is equal to 1 over t squared times the integral of t cubed minus t squared plus t dt plus c naught. Okay, and if I do that integral, I get a fourth order polynomial, and then I'm dividing that fourth order polynomial by t squared out the front, and I'll leave you to do the algebra to get the final result, which is simply t squared over 4 minus t over 3 plus 1/2 plus the integration constant divided by t squared. Okay, so the first I think question in this workshop is probably the easiest. It is important that you know how to identify linear ODEs. Okay, and once you've identified a linear ODE, remembering that you solve that with an integrating factor. Okay, so question B here, well, we have an equation that I can immediately see is not going to be separable. Okay, so you should always check that if an equation is separable. I can immediately see it's not going to be linear either, because in both x and y here I have some non-linear terms, so it's not going to be a linear equation. So the next logical thing to check is whether or not this is an exact equation. Okay, so what I'm going to do is I'm going to multiply through by dx to every term in this equation to rearrange this equation, just using a bit of algebra. Well, I get 2xy squared plus 4, so that's the left hand side, which is now being multiplied by dx. I'm going to bring the other term to the left hand side as well, so I get 3 minus x squared y dy equals 0. Okay, so here I have two so something that I can test whether it is an exact equation or not. So here I have this function m, and over here I have, including the negative, I have this function n. Okay, and I want to test if this is an exact equation or not, which of course means that I have to calculate the two partial derivatives. So the partial derivative of m with respect to y is equal to 4. Well, I bring this 2 down, so I get 2 times 2 is 4 times x times y. The partial derivative of n with respect to x, well, I bring this 2 down, so I get 2 times negative 2 times negative 1, so I get 4 times xy again. So okay, yeah, great, this is exact. Okay, great, so knowing that this is exact, I can try and find this function f, which is the integral, well, which if we take the partial derivatives equals m and n. Okay, so f is equal to the integral of m with respect to dx. Okay, so m was this this thing up here without the dx. So let's write that as the, so we write the integral, good junk here, we write the integral of 2xy squared plus 4 with respect to dx, plus some arbitrary function of y, okay, because remember that m is a function of x and y, and we're only taking the integral with respect to x here. So this is fairly simple. We're just going to get, this is a polynomial, a first order polynomial. So we're going to get a second order polynomial when I integrate that. So I get x squared y squared plus 4x as that integral there, plus some, again, plus our function of y, g of y. Okay, so now I want to take the partial derivative of f with respect to y, because that is equal to n, we know. Okay, so if I take the partial derivative of this thing that I just derived with respect to y, I get 2x squared y. The 4x disappears because it's got no, well, it's a constant in terms of y. But g is a function of y, so we must take a partial derivative of g with respect to y. Okay, and we know that this thing equals n, right? Because the partial derivative of this function f with respect to y is always equal to n. And n I can write as negative 2 times 3 minus x squared y. Okay, and the nice thing here is that you can see immediately that this term here, these two terms here are going to cancel. Okay, because there's a positive 2x squared y on both sides of the equation, so we can cancel those and end up with an expression for the derivative of g. So g prime of y is just going to be equal to negative 2 times 3, so negative 6. Or in other words, if I can integrate that and say g is equal to negative 6y. Okay, so now I have an expression for my function g. I can go back to this thing f here and use that in the equation. So f is equal to x squared y squared plus 4x plus g of y, which is negative 6y. Okay. The solution to the ODE is setting f equal to some constant. Okay, so f equals some constant c naught. So x squared y squared plus 4x minus 6y equals some constant c naught is the solution to the ODE. Okay. So moving on, the next equation we're faced with, well, again, we should try to identify what it is. It is obviously non-linear because I have this y squared term here, and y is the dependent variable. So it's obviously not separable, so it's not separable, it's not linear. I could check if it was exact, but actually I don't really need to, because I can already see that this is in the form of the Bernoulli equation. So this is a Bernoulli equation. Okay, so you need to know, you need to be able, I think that has two L's. You need to be able to identify a Bernoulli differential equation, okay? Basically, if this term y squared wasn't here, if this term y squared wasn't here, this would be a linear equation, but we have a right-hand side which is multiplied by some power of y, the dependent variable, so we have a Bernoulli differential equation. Okay, so to solve a Bernoulli differential equation, we know that we can make a substitution. Okay, and the substitution is usually u is equal to y to the power of 1 minus n, where n is the power of this, well, not of the t, hang on. N is the power of this, of the y on the right hand side. So 1 minus 2 is negative 1. So our substitution is going to be u is equal to y to the power of minus 1. Okay, so I can write that as, well, I can write that in two ways. I can write u is equal to 1 over y, or y is equal to 1 over u. Okay, well, what I need, or what I have in the differential equation, is dy by dt. So I need to be able to write dy by dt using the chain rule is equal to dy by du times du by dt. Okay, well, this first term in the chain rule I can obviously easily calculate. I just take the derivative of y with respect to u. So this y is equal to 1 over u. If I take the derivative of that with respect to u, I get negative 1 over u squared. Great. So now wherever I see dy by dt, I'm going to replace it with negative 1 over u squared du dt. Wherever I see y, I'm going to replace it with 1 over u. And wherever I see y squared, I'm going to replace it with 1 over u squared. Okay, so let's do that now. So in my ODE, I have dy by dt, so I'm going to replace that with negative 1 over u squared du by dt, plus 4 over t times y, so this y here on the left. Well, wherever I see y, I said I'm going to replace it with 1 over u. And then on the right-hand side here, I get t cubed times y squared. So I get t cubed, y squared I said I was going to replace with 1 over u squared. Okay, great. So now I just need to write this in the standard form, in the normal form. So I'm going to multiply this equation by negative u squared, because if I multiply by negative u squared, this term in front of the du by dt will become 1. So I get du by dt, this is going to be minus u squared times 4 over t times 1 over u equals minus t cubed 1 over u squared times u squared. I can simplify that, of course, so du by dt minus 4 over t times u equals negative t cubed. Okay, and so this is now a linear equation. With u being the new dependent variable. This is a linear equation. I'm going to solve it using integrating factor. Okay, so can't scroll, there we go. Integrating factor, so here my function p of t is equal to negative 4 over t. My integrating factor is going to be the exponential of the integral negative 4 over t dt. So this is just simply going to give me t to the power of negative 4. Okay, then I can use that integrating factor to solve for u. Okay, so u is equal to 1 over mu of t, so 1 over t to the power of negative 4, times the integral of, well, mu, so t to the power of negative 4, times the right hand side, which is negative t cubed, dt, plus some integration constant t naught. Okay, well, we can simplify this, right? So I'm just going to write 1 over t to the power of negative 4 is just equal to t to the power of 4. T to the power of negative 4 times t to the power of 3 is just t to the power of negative 1, or, well, I have a negative here as well, so negative 1 over t. Okay, so that's just t to the power of 4 times, well, this is just going to be the logarithm, right? So 1 over the integral of 1 over t is log, so I'm going to get negative log of t plus some integration constant. So this is u. U is equal to this thing. So we have a solution in terms of u now, a general solution to this ODE. We want to write this u and this solution in terms of y, but recall that y is just simply equal to 1 over u. So y equals 1 over u. So finally we get, therefore we get y is equal to 1 over that thing. Minus log t plus c naught. Okay, so using that Bernoulli, or I guess recognizing that that was a Bernoulli ODE, we were able to use the substitution to turn that into a linear ODE in the substitution variable, solve it using an integrating factor, then transform back into the original variable. Okay, moving on to question D. I can immediately see that this is not a separable equation. You can try that if you like. I can see it's not a linear equation due to the fact that x is squared in some of those terms and y is also squared in some of those terms. So there's no way I can write this as a linear equation. Let's check if it is homogeneous. Okay, so my functions, check if it's exact, sorry. My functions m and n here, let's check the partial derivative of m with respect to y. So if I take that partial derivative, I get 2xy plus 3 times y squared. If I take the partial derivative of n with respect to x, then I get 2xy. So unfortunately I don't have this term here, so these are not exact equations. This is not an exact equation. But it might be homogeneous, so we should check that. So to check if an equation is homogeneous, we need to check these two functions m and n evaluated at tx and ty. So wherever I see an x here, I'm going to write t times x, and wherever I see a y, I'm going to write t times y. So m is x squared y squared, so x is now x times, or t times x. Y squared is now t times y squared plus y cubed, so now that's t times y cubed. N is x squared is t times x squared. Y is t times y. Okay, if you see here, in each term, I have a t here and a t squared here, so that's a t cubed. I have a t cubed here, so this is actually equal to t cubed times m evaluated at xy. And similarly, I have a t squared and times a t here, so I have a t cubed there as well. So t cubed times n of xy. We have the same exponent in this t here, so we actually have the ODE is homogeneous. Alright, so that means that I can use a substitution. Y is equal to u times x, where u is the substitution variable. I need to be able to write my differential dy, if I can scroll up, my differential dy here in terms of x and u now. So because y is a function of two variables, dy is going to be equal to the partial derivative of y with respect to x times differential dx plus the partial derivative of y with respect to u times du. And of course these are very easy to calculate because these are very easy to calculate because y is just some very simple function of x and u. So the partial derivative of y with respect to x is just u. And similarly, the partial derivative of y with respect to u is just x. Okay, so now in my equation, in my ODE, wherever I see y, I'm going to write u times x, and wherever I see dy, I'm going to write u times dx plus x times du. Okay, so let's do that. Okay, so I get x times y squared, so now I get it's ux squared plus y cubed, so that's ux cubed times dx plus x squared times y, so that's ux times dy now. So dy is now this thing u times dx plus x times du. And that whole thing is still equal to 0. Okay, so I have a lot of common factors here. So what I will do is I'm going to divide through by, well, let's divide through by this common factor u times x, because I have a u times x here, I have 3 of them here, and I have 2 of them here. So let's divide through by u times x. So I'm going to get x times u times x, so I'm going to write that as x squared u. Here I'm going to get u times x squared, so I'm going to write that as x squared times u squared dx plus, well, the ux here cancels, so I get x squared times u dx plus x du equals 0. Okay, in this equation I have a common factor of x squared, so let's divide through by x squared here now. A common factor of x squared in these things. So if I divide through by x squared, on the left I get left with u squared plus u dx plus, on the right, u dx plus x du equals 0. Okay, and now I can combine these dx terms here to be written like so. So I get a u squared plus 2 times u dx plus x times du equals 0. Alright, so hopefully you can see that this equation is in fact separable. So what I'm going to do is divide through by both of these terms that I've highlighted here. So if I do that, then I get dx over x plus du over u squared plus 2u. So u squared plus 2u I'm going to write as u times u plus 2. And then I can integrate both sides of, well, I can integrate each term in that equation, right? And I should be able to find a solution in terms of u. Okay, well, the first integral, of course, is just a log of x. The second integral is a little bit trickier, so here we have to use the idea of partial fraction decomposition. So we're going to be returning to this in a future class, probably after the mid-semester break. But maybe you might like to revise partial fraction decomposition in your own time. But what it basically says is if I have a function 1 over u plus 2, I can write that as some number a over u plus some number b over u plus 2. And I want to find out what the value of a and b are. So I'm going to multiply both sides of this equation by the denominator on the left-hand side. So on the left-hand side I get left with 1. On the right-hand side I get something that looks like this. Okay. So now I want to find these values of A. I'm going to try just different values of U. So firstly I'll try U equals 0. Well, if U equals 0, the left-hand side is still 1. 1 is equal to A times 0 plus 2, so it's 2A, plus B times 0, so I get 0. So this tells me that A is equal to 1/2. Then I'm going to try U equals negative 2, because the left-hand side stays as 1. I get negative 2 plus 2 times A, so I get 0 times A is 0, minus 2 times B, tells me that B is negative 1/2. Okay, so therefore 1 over U times U plus 2 can be written as 1 over 2U minus 1 over 2U plus 2. Okay, so this is much easier to integrate, right? Because now I can integrate, instead of this challenging thing to integrate, I can integrate 1 over 2U minus 1 over 2U plus 2 du. Okay, because that's just two logarithms, okay? And okay, the whole thing has to equal 0. So we end up with the log of x plus 1/2 times the log of u minus 1/2 times the log of u plus 2 equals some integration constant which I'll call C0. Great. Okay, so what I can do here is I can take the exponential of both sides of this equation. So if I do that, if I let e to the C0 be equal to some other constant C1, because if I take the exponential of a constant, it's still just equal to the it's equal to some other constant, so I'm just going to call that C1. The left-hand side is quite interesting because I get the exponential of the sum of these three terms, which I know I can write as the product of these three terms. So I can write this as e to the log x times e to the half log u times e to the minus half log u plus 2. Okay, but we also know that logarithm and exponential are inverse functions of one another, so we can simplify this again to read x times u to the half times u plus 2 to the minus a half. Okay, and that was equal to C1, constant C1. Okay, well, I really would prefer u to not be have any square roots in it, so what we're going to do is we're going to let C2 equal to C1 squared, because we're going to square both sides of this equation. Okay, so I'm going to have x squared times u over u plus 2, so just taking that negative exponent to the bottom, equals some number C2. Okay, I have a solution in terms of u here. I can write that in terms of y now, because y, if you recall, all the way up here is equal to u times x. So u is just equal to y divided by x. So wherever I see a u here, I can write x squared times y is equal to u divided by u is equal to y divided by x. So I can write y divided by x over y divided by x plus 2 equals some constant C0. Okay, and while this is a solution to the ODE, you can simplify this algebraically, but I'll leave you to do that in your own time, because, well, this video is already getting quite long. Okay, so question E I can immediately see is not going to be separable, and it's not also going to be linear. You can also check that it will not be exact or homogeneous. Well, it's pretty straightforward to check that, so maybe you might like to do that. But I can actually see that an obvious choice here is to make the substitution u is equal to x plus y plus 1. Okay, and the reason that is because if I look at du by dx, I get 1 plus dy by dx. Okay, because if I take the derivative of x, I get 1. If I take the derivative of y, I get dy by dx, and if I take the derivative of 1, I just get 0. Okay, so du by dx is equal to 1 plus dy by dx. Okay, but dy by dx is the ODE itself. Okay, so dy by dx is equal to negative x plus y plus 1 squared. Okay, but we were calling this thing x plus y plus 1, we were calling that u. So dy by dx is actually equal to negative u squared. Okay, so I can rewrite my equation du by dx equals 1 minus, in fact, 1 minus u squared. Okay, let's multiply that whole thing by negative 1. So just to write that as du over negative dx equals u squared minus 1. And then let's rearrange this equation, because in fact this is separable now. So this is a separable ODE in the variable u. Okay, so we get du over u squared minus 1 equals negative dx. Okay, and I can integrate both sides. The right hand side is of course just negative x. The left hand side is a little bit tricky, so we should check our table of integrals. Okay, so if I just leave full screen mode here, where is my table of integrals? Okay, on our stream page, we have one subset called one subheading called Final Exam, and we have a document called Useful Information provided with the final exam. Of course, this is sort of from last year, but of course you can always print this out and have this next year during tests. If we scroll down, we can find a table of integrals, well, table of derivatives and a table of integrals. And you may be able to see that this integral number 5 here, this is exactly the form that we have, except for u is the variable rather than x, and our a squared is just equal to 1, so a is just equal to 1. So in fact that integral that we were looking at before is just going to be equal to 1 over 2 times a, so 1 over 2 times the log of u minus 1 over u plus 1. Okay, so we're simply going to get this integral here is going to turn into 1 over 2 times the log of u minus 1, u plus 1. The right hand side, of course, is the integral is just negative x plus some integration constant. Okay, well let's multiply that whole thing by 2 to get rid of the 1/2 on the left side, and then we'll take the exponential, so we get on the left hand side the exponential and the log will cancel out. So u minus 1 over u plus 1 is equal to the exponential of negative 2x times c1, where c1 is the exponential of 2 times c0. It's just some constant. Okay, well, okay, so this is the solution in terms of u, but u is equal to x plus y plus 1. So u minus 1 is just equal to x plus y. U plus 1 is just equal to x plus y plus 2. So we can rewrite this in terms of y now, this differential equation. So u minus 1, x plus y, over x plus y plus 2 equals c1. I might write this as c1 over e to the 2x. And again, this is a fine solution to the ODE, but I can actually rearrange this for y, so maybe I'll do that quickly. I can multiply both sides of the equation by this denominator, x plus y plus 2. And I get something like this. Now what I might do is I might just take that common factor of x plus y to the left hand side, so I might get x plus y. I've got 1 on the left hand side, and I've got minus c1 over e to the 2x on the right hand side. Okay, so I can divide through by now this bracketed term on the left hand side here to find x plus y equals 2 c1 over e to the 2x times 1 over 1 minus c1 e to the 2x. I can subtract x from the left hand side and simplify the right hand side, in fact, so I end up with y is equal to 2c1 over e to the 2x minus c1. Okay, so I can find an expression, minus x, don't forget the minus x. I can find an expression for y explicitly here. Okay, fantastic. Moving on to f. So again, I'm running short on time. This is quite a long video. I can already see this is not going to be linear or separable. I'm going to leave it to you to check that this is not exact. Well, it's not actually so hard, right? But this is, maybe I'll do it real quick. M and n, my is equal to 4y, nx is equal to 2y, so not exact. In fact, you can easily show that it's not going to be homogeneous, even just looking at the first term here. So this is going to be 2 times t squared y squared plus 3 times t times x. So this is not equal to t to some power m times t at x, y. So this is not homogeneous either. Okay, but in fact, one thing I can notice is that if I look at this ratio, my minus nx over n, well, this is 4y minus 2y over n, which is 2xy. Okay, well this is 4y minus 2y is 2y over 2xy. We've got a common factor of 2y, so I just get 1 over x. So this ratio is a function of x only. So I can use an integrating factor. Okay, I can use integrating factor. Okay, so my integrating factor is going to be a function of x only, which is going to be e to the integral of this thing my minus nx over n dx. Okay, this is just equal to the exponential of the integral of 1 over x dx, which of course the integral of 1 over x is just the log of x. The exponential of the log of x is just x. So I just get the integrating factor mu is equal to mu is equal to x. So I can multiply my original ODE by x. So I get 2y squared times x plus, what was the next term? 3x, so 3x squared dx plus, now my dy term was 2xy, so it's going to be 2x squared y. 2x squared y times dy equals 0. And actually, funnily enough, this is now exact. Okay, so if I check, this is my new maybe I go my new m and my new n. My is now going to be 4xy. Nx is going to be 4xy. So now this equation is exact. So we can solve this in the same way we did, what was it, question B, I think. So in fact, I'm going to leave you to do that and just show that the result is x squared y squared plus x cubed equals some constant c naught. Okay. If you have any problems with the analysis from I guess the steps that I've jumped there, just let me know and I can do that in more detail. But again, this is something that I would expect you to be able to do in this class. So I guess in this workshop we've already solved an exact equation, so I've given you an example of that. Okay, and now if I go to the final question, G here, well, this is actually a linear equation. Minus y over 2 equals 2 sine of 3x. So this is linear, so we're going to use an integrating factor. I'm going to use an integrating factor here, right? So that's not too hard. So let's really quickly look at what that integrating factor would be. So we're going to look at the exponential of the integral of a p of x, which is actually just going to be minus a half, right? In our case. So our integrating factor is actually e to the negative x over 2. Okay, and so what makes this problem slightly different is when I write out the solution, I get 1 over e to the minus x over 2 times the integral of, well, what was the right hand side? 4 sine of 3x times this integrating factor. Okay. Plus some integration constant c naught. So what makes this problem a little bit challenging is you have to solve this this integral using integration by parts. So this integral here we solve using integration by parts. Okay, and so again, this question is really just there to give you a reminder of or an encouragement to really revise your integration and your differentiation from first year calculus. Okay, so this is a first year calculus problem. I'll leave you to do that, and the solution is in the worksheet. The worksheet solutions, which is a PDF on the stream site. But again, if anyone has any problems with evaluating this integral, let me know. Okay, thank you very much. I'll see you next week.